Welcome back to the deep dive. Today we're doing something I think is really fascinating. We're taking a look under the hood of how world-class software is actually built.
Hmm.
And this deep dive, it isn't about if your Python script runs, but how professionally it runs.
Right.
We're focusing on turning that quick piece of source code into something that's reliable, collaborative, and this is the crucial part, maintainable.
That is the mission, and it's such a critical one. We've been handed this internal playbook, really, a set of best practices, literally called codingbestpractices.md.
Okay.
So we're just tearing through that to pull out the key things you need on style, type safety, testing, automation. Think of this as the shortcut.
A shortcut to avoid all the painful code review feedback.
Exactly. All of it.
I love that. Okay, so let's lay out the roadmap. We're trying to standardize the whole professional pipeline, right?
Yeah.
So first, we'll tackle the aesthetics, how the code looks and feels. That's style. Then we'll get into the internal safety features, making sure it's accurate before it even runs.
Which is typing.
Typing. Third, how the code communicates with other developers, documentation and structure. And finally, that assurance layer, the tools that guarantee it all just works.
Testing and automation. Let's do it.
Let's start with style. If you're a solo coder, style feels kind of subjective.
It does.
But the moment you bring on a second person, consistency becomes this essential social contract. And in professional Python, that contract is
It's PEP8. That's the one.
PEP8.
Exactly. And PP is not just a list of preferences. It's really the common language of Python.
The lingua franca.
Right. When someone is reading your code, you want them focused on the logic, not, wondering why you use tabs instead of spaces. It speeds everything up. You eliminate all those pointless arguments.
And let's pull some specifics from the source that every developer needs to implement, right now.
Okay, top of the list is naming. Just use meaningful descriptive names for everything. Your variables, functions, classes.
So no more df4 or data frame.
Please, no. If it's customer data frame, there's zero guesswork. It just reduces the mental load immediately. Second, indentation. Strict consistency.
Always four spaces.
Always four spaces. And the absolute rule, never, ever mix tabs and spaces. That just leads to these bizarre, invisible bugs. It's a nightmare.
And what about that rule for blank lines? I feel like that one gets overlooked a lot.
It does, but it's so important for readability. The document is clear. Use 2 blank lines between your top-level functions and classes.
Okay, 2 lines.
But only 1 blank line between the methods inside a class gives the code a rhythm, a visual structure, and of course, the naming conventions. Snake case for your functions and variables, and capitalized names, camel case, for classes.
That sounds like a lot of rules to manually police. Am I supposed to sit there counting blank lines all day?
Absolutely not, no. This is where the modern tools just save us. It's all about automation. The source mentions linters, things like Pylint or Flake8, which find the violations for you. But the real game changer, and what every professional shop uses, is an auto-formatter, specifically black.
Okay, so why black? Why is that so much better than just a linter that yells at you?
Because black is, and this is their term, uncompromising. It removes all subjectivity. You just run it. You write your code to work, and black handles all the formatting to PP8 standards automatically.
So every file in the project looks identical.
Exactly. It doesn't matter who wrote it. It just transforms formatting from this manual chore into an automated, non-negotiable step. It saves so many hours of arguments.
That brings us really nicely from the code's appearance to its actual behavior. Python's loved for its flexibility. It's dynamically typed. But as a code base gets bigger, that flexibility can become a huge liability, can't it?
It absolutely can. That lack of context means a subtle error, like passing a string where you expected a number. It doesn't show up until that line of code actually runs.
Which could be weeks later in production.
Exactly. It makes big systems really error-prone and hard to maintain.
So the solution is type hints. They were introduced back in Python 3.5. They don't change how Python runs, but they add this missing metadata for developers and for other tools.
Precisely. We can do simple types, A int, B int. But for the complex stuff, we need the typing module. This is where you see the capitalized types like list, dict, tuple.
Okay, let's walk through that because this is where it gets really powerful. Say a function returns a dictionary where keys are strings and values are lists of floats. How do you even write that?
You just build it up with the typing structures. It would be dict.sty, list float. You're communicating the container type and what's inside it. It's incredibly precise.
And what about handling real-world data where something might exist or it might just be none?
That's where you use optional C***. It signals that, yes, it could be a string, but none is also a perfectly valid value, or if it could be one of two types, like an integer or a float, we use unit float.
Ah, and the document highlights some more modern syntax for that, which I think is important.
Oh, it is. If you're on Python 3.0 or newer, you should just use the pipe operator, the vertical bar.
So instead of unit float, you just write.
In float. It's purely a style change, but it makes the type hints look so much cleaner, much more part of the language. It's a huge signal you're up to date.
But again, these are just hints, right? The Python interpreter itself just ignores them. How do we make this a real safety net?
That's the crucial next step. It's type checking. And that's driven by a third-party tool called MyPy.
Okay.
You run MyPy on your code, and it analyzes it statically without running it, and just reads your type hints and looks for any inconsistencies. It basically makes Python behave like a statically typed language before you even execute it.
I thought the source document's emphasis on MyPy strict was maybe the most compelling point in this whole thing. What does that strict mode actually guarantee?
It guarantees reliability. Running MyPy in strict mode forces you to annotate everything and do it correctly. The quote in there is powerful because it's true. If your code passes MyPy strict, you've essentially proven that there are no accidental type errors in your system.
You've just eliminated an entire category of runtime bugs.
An entire class of bugs gone. It's the highest bar you can set for type safety in Python.
And we should mention the disallow untyped defs flag, too.
Absolutely. That flag makes sure you don't accidentally skip the process by just, writing a function without any hints at all. If you're serious about quality, you need these strict controls.
So we've covered how it looks with black, how safe it is with MyPy. Now, communication. How do we make sure a developer can understand what your code does without reading every single line?
That is the job of docstrings.
Yeah.
Docstrings, enclosed in triple quotes, they are the summary. They explain the function's purpose, its arguments, what it returns. But here's a key insight from the source. The most powerful part of a good docstring is a concrete example.
And that leads directly to a tool that links documentation with reliability. Docdist.
Docdist is brilliant. It's built right into Python. It finds those examples in your docstrings, the ones that look like you're typing in a Python shell, and it runs them as tests.
So if the example in your documentation is wrong,
A test fails.
that's amazing. So you're basically turning the documentation you have to write anyway into a free, self-validating test suite.
Precisely. And if you run python-m docdist mymodule.py and get no output, you know your docs are accurate. And for anyone starting out, the docs mention tools like the AutoDocstring VS Code extension to help generate the boilerplate.
Okay, so beyond individual functions, let's talk project structure. Refactoring code into clean units.
Yes. Organizing code into modules, your .py files, and packages, which are just folders with an init.py file inside. This structure is essential, but it all depends on clean import rules.
Which brings us to what feels like the cardinal sin of Python development, the wildcard import. The top.
Yes. It's so toxic to a clean code base.
Why, though? Why is it so bad?
Because it just pollutes your namespace. When you import everything with an imbu, a reader has no idea where a name came from. Was it defined here? Did it come from that other package? It forces you to trace everything back. It's just a mess.
And a quick reminder on the entry point of a script. Always use an import guard.
The famous if name main block.
Right.
It ensures that when your module gets imported by another script, the code inside that block doesn't just run by accident.
And maybe just a quick word on absolute versus relative imports.
Sure. Absolute imports use the full path from the project root. They're clear. They're the standard. Relative imports use dots, like dot for the current package. They can be handy inside a package, but you have to be careful with them.
Okay, we've got the standards, the safety, the clarity. Now for the layer of assurance. Testing. Testing isn't just about catching bugs. It's about making sure that when you add a new feature, you haven't broken something that was working yesterday.
You could, in theory, just use the simple assert statement for basic checks. But that gets out of hand really fast. For real professional work, you move straight to PyTest.
PyTest is everywhere now. But for someone who's maybe used to the older Unitest framework, why is PyTest mandatory for modern development?
Because it just removes so much of the boilerplate. PyTest automatically finds your test files and your test functions. You don't need to create classes or inherit from anything unless you really want to.
So it lets you focus just on the test logic itself.
Exactly. It's faster to write, easier to read, and way easier to maintain.
Okay, so once PyTest is running, how do we know if we've tested enough? How do we measure that?
That metric is code coverage. Coverage is just a count of how many lines of your source code get executed when your tests are running.
Now, it doesn't mean your tests are good tests.
No, it's not a quality metric,
Oh.
but it tells you what parts of your code your tests are hitting. It's an early warning system. If coverage drops after a change, you know you missed updating a test somewhere.
And the tool for that is the PyTestCov plugin.
Exactly. And the source has a really useful tip for real-world projects. The hashtag pragma, no cover directive.
Ah, for code you can't easily test.
Right. Like some weird platform-specific code, you can just mark that line, and the coverage tool will ignore it so you can still aim for high coverage on the code that really matters.
Finally, we need the glue to hold all this together. Automation. Running Black, then MyPy, then PyTestCov. It's a lot of commands.
And that's where the makefile comes in. A makefile just lets you use the make tool to standardize your whole workflow. You can define a target, like make check, and have it run that whole sequence of commands with one single word.
And here we have to pause for a moment of shared developer trauma. What is the single most bizarrely strict yet totally fundamental rule of a makefile?
The command under a target must start with a tab character.
A literal tab, not spaces.
Not 4 spaces, not 8 spaces, a tab. It's this relic from decades ago, and it has cost every single developer hours of their life debugging a build that fails for no apparent reason. It's a rite of passage.
It really is. And the last key concept for makefiles is the .fony target.
We use phony to mark targets that aren't actual files, like clean or test. If you didn't, Make might get confused if you had a folder named test. Marking it. PHOI guarantees make test runs the commands you want every single time. It's the final piece of the puzzle.
This has been an incredibly detailed look at moving from just, scripting to building professional-grade software. We've built this whole pipeline, Black for style, MyPy in strict mode to kill runtime errors.
Doc strings and doctist for self-documenting APIs.
And then PyTest and Makefiles to stabilize and automate the whole thing.
We've basically laid out the toolkit for, near perfection code that passes MyPy strict and hits very high code coverage. But we all know professional development is a trade-off. It's quality versus speed. So for you, the listener, as you tackle your next project, knowing the constraints of real-world deadlines, what is the minimum threshold of automation and quality you'll actually implement? Which makefile targets format, tests, lint will you set up first? And what's the lowest code coverage percentage you'll accept to make sure your project has quality but still gets delivered on time?
Something to ponder as you start building your own professional pipeline. Thanks for diving deep with us.